And hello and welcome to this Co-UDlabs webinar. We've been doing this project for some 4 years now, and we're reaching the end. The next few months will see the final outputs from Co-UDlabs. And so this is our last webinar, where we're going to be sharing some of the research findings, but particularly today we want to make sure people understand where you can access this information going forward. I've been on the team for the last 4 or 5 years, and I will be moderating today. Now, the agenda that we're following this morning is basically covering 3 main areas of research that we have undertaken as part of Co-UDlabs. We're starting off with our activities on smart sensing and monitoring in urban drainage. And essentially what this is about is new technology and methods, and also about how we work with digitalization and how we create a more sensitized and evidence-based decision-making going forward. The second session is covering evaluation of asset deterioration in urban drainage systems. And here we're looking at how we can update and improve the work that's done on defects, particularly pipe work, as that is fundamental to drainage systems and sewerage systems, and looking at how do you increase their durability and their sustainability. And to do this, we need to consider the fact that they age. We've got to adapt to climate change, and also we've got a lot of what we call disorderly urbanization going on, which all of these systems have got to fit within. Then the third session is looking at improving resilience and sustainability. And for that, it's about having efficient, sustaining and good performing systems, and how do we address consequences of things like pollution and flooding and urban vulnerability to extreme events. Now, as a reminder of Co-UDlabs, what this actually is, Horizon 2020, and it has brought together 7 research institutes from around Europe. And the purpose of Co-UDlabs was to get us working together to address the common issues and to look at how we can learn from each other and how we can, in future, as urban drainage research facilities, encourage collaboration at the international level. And we're supported by Euronovia, who are running the webinar today, and GRAI from France, to give us some of the support that we needed as research institutes to deliver this project. Co-UDlabs has had 3 key goals over the last few years. The first, as I've mentioned, is fostering cooperation, providing networking. The second, and what has been perhaps the largest element of it, is to facilitate transnational access. This is exchange and collaboration. Under the rules, somebody from Germany could apply to do research in any of the other facilities, but not the one in Germany, and vice versa. The Brits had to go to mainland Europe to do their research. And the transnational access has resulted in a huge amount of practical work research undertaken, some of which we're illustrating in the events that we are holding this, or the presentations we're doing this morning. And that is what that is about, is that we had 3 joint research activities. Those are covered by the 3 sessions. And this is where we, as the research organizations, undertook work with each other to address particular issues. Now, the transnational access, I've just put a few figures up here to remind people that we ended up with 227 different user groups from 26 countries. They're illustrated here. And 11 of those were non-EU. And we, as a result, were able to undertake a real variety. It ranged from green roofs through to testing the water hammer effect of pressurized sewers on rehabilitation techniques. And as we're now reaching the end of this research, I'd just like to highlight that going forward, we're creating a new community. So UDrain, there's a web link at the bottom there. And by the way, we will be sharing all of the slides at the end of this meeting this morning. We're creating this UDrain. It's working with the International Water Association and Joint Committee. And we've started there by putting together an inventory, an atlas of research infrastructures that are available in Europe and around the world. We want to build a community, and a lot of it's about enhancing uniform practices. This is one of the things we found early on, is that we all do things slightly differently in different countries, and there is a need for sort of harmonizing and ensuring that we work in a uniform manner. We want to share results, we want to work together on studies, and the intention is to organize further congresses and webinars and other training. And of course, we are looking as well at further EU funding to take forward the collaboration that we have already started. So, a reminder of the agenda, we will start off with session 1. Each session is 1 hour. We have the leader of the joint research activity introducing it, and then we have 2 relevant presentations that explain in a little more detail some aspects of the research that's undertaken. And at the end, there is a 15 minutes for questions and answers. We would ask that if you want to raise a question, please post it in the chat on the screen, and then we can ensure that we try to answer that. At the end of session 1, there is a short coffee break. Session 2 again, 1 hour, 3 presentations and a discussion, then a coffee break, and we finish with session 3, 1 hour, 3 presentations and a series of questions. So at this point, it's time to start session 1, and I'm going to stop sharing and hand over to Jean-Luc from INSA Lyon, who was the lead for that particular work packet or joint research activity. So Jean-Luc, I've just stopped sharing. If you'd like to take over the screen.
Yeah. Thank you. Hey.
Yeah, we can see it full screen.
Yeah, thank you. Good morning to everybody. We are happy to have you this morning as participants to these presentations of key findings. I have to move this. Oops. And I will introduce briefly the Joint Research Area 1, or also named in the project Work Package 6, which is easier to say, which is about smart sensing and monitoring in urban drainage. We had 5 partners involved in this part of the project: EAVAG in Switzerland, the University of Sheffield in the UK, University of La Coruña in Spain, Deltares in Netherlands, and INSA Lyon, where I am working in France. So this work package was about sensing, monitoring, and how to improve these aspects in urban drainage, going from data collection, monitoring, data processing, data quality assessment, and in the last step, to analyze and interpret data and to learn new things and develop the knowledge about our systems. And this work package was divided in 3 main tasks. Task number 1 was about identifying and evaluating new sensors and technologies for hydrology and hydraulics, pollutant load monitoring, and urban drainage underground asset inspection. We know that it's a growing field. We have every 6 months we have new sensors on the market, traditional sensors. We have also development of new technologies based on IoT, low cost or low tech technologies, interactions between sensors. So the field was quite wide, and we wanted to investigate a little bit this aspect. The task 6.2 is about definition and evaluating new methods and tools to improve evidence base for reliable and validated urban drainage monitoring data. In other words, the idea was to provide tools and methods for users to improve their metrology practice in the field of urban drainage. The task 6.3 was about defining and evaluating new methods to analyze and interpret urban drainage space and distributed data. In particular, the spatially distributed CSO structures in traditional sewer systems, and also the widely spread SUDs or source control measures that we have dealing with stormwater management in urbanized areas. Task 6.1 we selected was led by EAVAG, and we, at the end of a of a multi-step process, we started with a list of 55 sensors. We ended with 8, which were tested. On the right side of my slide, you can see the list of the 8 sensors which were tested by at least one of the partners. And these tests will lead to satisfactory or non-satisfactory results. And you will have more details in a few minutes by Pierre Le Chevalier. He will present much more detailed about this task 6.1. Task 6.2, we developed during the project a software tool coded with MATLAB, and the name is UDMT, Urban Drainage Metrology Toolbox. It's a set of coordinated tools, methods, which are implemented in an easy-to-use sensor, covering the whole chain from data acquisition after you have calibrated your sensor or you have correlated the sensor with traditional lab analysis. The second step is you collect raw data from your sensors and you transform it into corrected data based on the calibration and correlation functions established in step 1. Once you have raw corrected data, you can work one step further to assess the uncertainties in this data. And then you go in the step number 4 with the data validation, where different criteria of validation can be tested. And we've added a 5th functionality about tracing experiments as a tool to check and validate some discharge measurements in sewers. So this software tool was initially developed as a web app. It's available at this address. You can see on the slide. But we had many feedbacks from users, especially in municipalities or consulting companies. Oh, we don't want our data transferred on the internet. So we developed executable versions that you can install on your own computer, and which are exactly mimicking what the web app is doing. We have developed a detailed user manual with lots of examples that you can also download, so you can train yourself with this user manual by reproducing the examples which are described, because all the data files are made available. Today, we have more or less closed the version 2024B, and the final one, 2025A, is planned for April 2025. During the last days, we made some final cleaning of the code, revised the user manual, and corrected some minor final bugs we discovered recently by feedbacks of some users. So the very final version will be available very soon, 2-3 weeks from now. I will not enter into more detail today because this UDMT toolbox was the topic of several presentations, webinar and training courses organized since 2022. And we use these sessions to get feedback from users for debugging and improving the tool. And you will find the links on the slides, and I invite you to go on this website to download the tool and try to work with it. You will also have access to former webinars that have been recorded, and just be patient for 2-3 more weeks until April 25 for the very final version. In task 6.3, about distributed monitoring and data interpretation, it was led by University of Sheffield. It was about the analysis of spatially distributed urban drainage large data sets. Frequently, the operators, the consultings, they are working on some catchment, sub-catchments, but a very wide-scale analysis is rarely done, and this is what we wanted to investigate. We focused a lot because some data are available in some regions and countries in Europe, which is not the case everywhere. But we focused on an example of CSO data collection and performance assessment available in England and Wales, correlation analysis, and we also worked a little bit on how to compare the methodologies and the approach to deal with spatially distributed data between CSOs and source control measures for stormwater management. And what are the lessons we can take for the future from these experiments? And you will have much more information about task 6.3 by Alma Skerlat also in a few minutes in this session. One of the main goals of this webinar today is to help you to find the Co-UDlabs information. So on this slide, you will have access to the slides and to the addresses, the links in the near future. After this webinar, you will find all the deliverables about sensor testing, the UDMT user manual, and the report about space-distributed monitoring data on the Co-UDlabs website. You will also find there all the publications. You will also be able to download the UDMT software on another link. And all of these links will be ready between April and May 25, May being the very ultimate deadline. So we invite you to have a look at the moment and come again in the near futures where all final deliverables will be made available. Another key aspect of Co-UDlabs was implementing, open science and open data sets. So all the data sets produced during the Co-UDlabs projects with testing the sensors, the code of the UDMT, everything is available on the Zenodo community repository based on the Co-UDlabs project. And again, you will find everything updated by April, May 25. We will invite you to go there if you want to access also to the reports, but which are also available on our website, but more important to all the data sets generated by the project. Yeah, thank you. This is the end of my introduction, and I give now the floor to Pierre for more information about task 6.1.
Thank you, Jean-Luc. Okay. Amazing. Is it all good?
Yep, that's fine.
Amazing. So yes, welcome to this morning's first part of the webinar. My name is Pierre Le Chevalier. I am working at EAVAG, the Swiss Institute for Water Research. And in the Co-UDlabs project, I contributed mainly to the task 6.1 of the project, which is about identifying and evaluating new sensors and technologies for the monitoring of urban drainage systems. And so today I will give you a nice overview about the results we produced during this task. And I will try to help motivating you to have a look at our deliverables if you want to have more information. So first of all, why is it so important to monitor in a better way the urban drainage systems? So the role of the urban drainage systems, as you know, is to bring polluted water from their source of emission all the way to treatment facilities. This task has two aspects. The first is to ensure that we protect the environment. So it's what we call the quality aspect of urban drainage systems. So we want to bring badly polluted waters all the way to treatment facilities. But urban drainage systems also have another aspect, which is about quantity, because those infrastructures are not only handling urban wastewaters, but they're also handling stormwaters, so the waters that fall from the sky when it rains. And it can happen that lots of water all of a sudden enter the urban drainage systems. And so basically, those two aspects, handling a quality and a quantity of the water, needs to be performed by those infrastructures. Now, if we want to do this in a better way, if we want to avoid emission of polluted waters into the environment and also better treat them, it's actually a good idea to have a better monitoring of those systems and a better monitoring of the quantity of water in the systems and also of the quality of the water in those systems, as well as monitoring the infrastructures in themselves. So seeing if the pipes are well maintained or if there are some holes or cracks in them and so on. Better sensors are also important, as I showed on the picture on the left, because sewers are really a nasty place and we would like to avoid as much as possible to send manpower inside. So if we can replace someone with a sensor, it's always beneficial for everybody. The urban drainage systems also rely a lot on big like pumps or valves, and those mechanic elements can be improved, or the management of those elements can always be improved with better knowledge about the inside of the sewers. For instance, if you know how much water is in the pipes at this time, you can improve the functioning of pumps. However, it would be nice to better monitor the sewers, but it's also quite challenging. As you can see on the picture on the right, when you put a sensor into the sewers, it usually has a bad time. The sensor can get clogged. It can get a biofilm growing on its window, which makes it actually extremely challenging to have lots of information about pollutants in the sewers. So as you know, in the project, we decided to test 8 innovative technologies to monitor the sewers. We started originally with a list of 55 sensors. As you can see, that were mostly focused on water quality and hydraulics, but also other aspects. Those 55 sensors were selected based on the opinion of all the members of the Co-UDlabs project. So everyone could basically propose a sensor to be tested, and we ended up with a list of 55 sensors. From this list, INSA and EAVAG, together we collaborated to reduce it to about 15 sensors. So this was done mainly based on our expertise. And once we have those 15 sensors, we asked again all the members of the consortium if they have interest in testing them, if they have the facilities suitable to test those sensors. And that's how we ended up with a list of 8 sensors, but also a list of facilities that are motivated and also that have the capacity to test them. All this process is also described in much detail in the deliverable 6.1 that you can already find online on this link. And so regarding the 8 sensors that we decided to test, we have a Proteus sensor, which measures coliform. We have LPICM, which means low power inductive conductimeter, which is a sensor which is able to monitor conductivity with a very low use of power. Then we have a sensor called the discharge keeper, which is a camera-based sensor able to monitor the flow. This is actually the only sensor that we tested that is aiming at monitoring quantities. The other sensors are for quality. Then we have 2 multi-sensors, multi in the sense that they are able to monitor different pollutants. We have ESA spectrometer, which is based on UV visible absorbance. We have the MVX hyperspectral imager, which measures visible and near infrared reflectance. We have a PAH sensor for the monitoring of PAH. We have the pipe mapping FSB, which is a technology able to make a mapping of the pipes. And finally, we also have a 3D LiDAR sediment mapping, which is a sensor able to map sediments in, for instance, pumping pits or in sewers. So all the sensors, in terms of methodology, we developed a very structured way to test them. So first of all, we decided to organize a first series of tests in our different facilities to assess the performance of each of the 8 sensors. In particular, we assessed different aspects of the performance which are listed on the rows of this table. We assessed the technological readiness level, so whether the sensor is already suited for an implementation in the sewers, or if it still needs some adaptation to be well functioning within the sewers. We also assessed how well we were able to test them. So if we have sufficient reference measurements, if we tested the sensors for long duration, so basically how robust our testing is. Then we quantified the operational performances of the sensor, which means basically how easy is it to install them, how easy is it to calibrate the sensors and to also just manage them during the month of trials. And finally, of course, we also assessed the technical performance of the sensors. So how is the range of the sensors? Is it suited for the sewer systems monitoring, and also what is the accuracy? All those results on this table is coming from the deliverable 6.2, which is not yet available online, but will be finalized pretty soon in April 2025. And now that you have a nice overview of all the sensors, I would like to zoom a little bit and to focus on two sensors. First of all, I will show you some of the results we obtained for the MVX. And then I will also show you some of the results we obtained for the ESA sensors. Yeah, so I guess let's go. So first of all, about the MVX sensors. So this is a hyperspectral camera. So basically, we are using a sensor which is a combination of a camera and a spectrometer. And the advantage of such technology is that we're able to measure spectral information of the wastewater surface with non-contact sensors. As you can see, for instance, on the picture in the middle, we did some laboratory tests of this technology where we placed some wastewater in this black cup in the middle. We used a light, and on the top, you can see here the camera that was actually monitoring the content of the sample. In terms of spectral resolution, the hyperspectral camera that we used is sensitive to the visible and near infrared range, which means between 400 and 1000 nanometers. The sensor is also encased in a metallic kind of box. So the camera is actually inside this box, which means that it's also suitable for application in the sewer systems. We had a field of view of 10 centimeters, and the sensor is able to estimate multiple parameters. And so in the framework of the test that we did for the Co-UDlabs project, we actually tested the sensors in 5 independent locations, one of them being the flume, which you can see on this picture on the left, on the right-hand side, sorry, where we put some water through this channel, which is kind of a kind of reproduction of what happens in the sewers. And we're also able to test the sensor in 4 other locations. And we used the sensor mostly to monitor turbidity. But today I will also show you a little bonus. I will show you also the performance of the hyperspectral camera for the monitoring of DOC, dissolved organic carbons. So let's have a look at some results. So on this slide here, I'm sharing with you, so as I mentioned, the performance of the sensor for turbidity on the top and DOC on the bottom. And each of the columns of this plot is a site where we tested the sensor. So one of the 5 sites. So for instance, you see the last column here is FL, which stands for flume, the sites for which I showed you the picture before. And what we quantified here with the box plots is actually the error of the sensor for the measurement of turbidity and DOC. So for instance, on the first box plot here, we see that for the site PK, the camera is able to estimate turbidity with an error with a median error of about 7%. And the range of error is between 5 and 10%. Okay, so if we look at the big picture now for turbidity, we see that in all the sites where we tested the methods, we are able to have a prediction error which is between 5 and 10%. In some of the sites, we even have error below 5%. So those results are really good because it means that with a camera, with the non-contact sensors, we're able to follow the turbidity level in the wastewater samples with an error below 10%. Now, if we look at DOC, we also have very promising results. For the Flume site, FL, we don't have this analysis done, but for the 4 other sites, we see that 3 of the sites have a precision of around 10%, which is also very promising. Again, I remind you, this is a non-contact sensor, so we are measuring from the distance, the level of DOC, with a median error of about 10%. There is only one site where the precision is slightly worse. All of this is discussed, and also the interpretation of those results is further discussed in the deliverable and in some of the publications that will be attached to the project. So I invite you to have a look at this if you want more details. Now, let me speak to you a little bit about the ESA. So this sensor is also a spectrophotometric sensors, but it is based on, this time, on UV visible absorbance between 200 and 735 nanometers. This technology, maybe you're already familiar with it. There are already some sensors that are using this measurement principle to estimate turbidity, chemical oxygen demands, nitrates, and so on. However, this sensor was particularly interesting for us in the project because it has a higher level of flexibility. So first of all, the sensor has an adaptable window. It is what I'm showing here or here. So basically, we can open or close the sensor and make this gap variable, which is very helpful if you want to adapt the sensor to each and every different wastewater type we are monitoring. Another really interesting aspect of this sensor is that it doesn't have a pre-installed model, but instead it has a flexible model, which means that we can always use the sensor for the monitoring of new pollutants. We just need to train a new model. So this flexibility is something that was really of interest for us. And also because the provider of the sensors, that they are telling that we are able to use it for the measurement of ammonium. And ammonium is actually a very key variable to monitor in the sewers and in wastewater in general. However, the technologies for the monitoring of ammonium are usually not performing the best. And so that's why when we saw this characteristic, the monitoring of ammonium, we were really interested in testing it. So you see here is some of the results provided by the manufacturers. Again, we tested this sensor in 2 locations. It was tested at EAVAG and later tested at the University of A Coruña in Spain. And yeah, let's have a look at some results. So in this slide here, I'm showing, first of all, 2 scatter plots, one for EAVAG and one for University of A Coruña. And those scatter plots are actually showing on the x-axis measurements, which is done in the laboratory with a reference methods. And on the y-axis, we are showing an estimation of ammonium done by the sensor. So basically, the closer the points are to the diagonal, the better the sensor is. And in both EAVAG and A Coruña, we see actually that the sensor is able to predict ammonium levels with satisfactory precision, let's say. And finally, on the right-hand side, we are showing the prediction of the sensor in blue, and the crosses are representing laboratory measurements. So basically, the left and the right side of the slide are just showing the same results, but in a different way. So overall, we can see that yes, we verified that the ESA sensor is able to follow ammonium concentration with a certain level of precision, and that this sensor has the potential to answer our future needs when it comes to the monitoring of ammonium in the sewers. Okay, so it's time to come to a small summary and conclusion. So I presented to you the MVX hyperspectral camera and the ESA sensors, which overall are quite promising technologies, even if there is still room for improvement. For the other sensors, you can see that some of them are also performing really well, while some others have showed worse performances. So yeah, if you are more interested in every single sensor and in all the details, I really would like to invite you to have a look at the deliverable that is coming quite soon, where we really discuss all this in much details. And if you have also questions, I will stay for the first session question, which is going to be conducted right after Alma's presentation. So now I'm done for this presentation, and I will give the floor to Alma.
Thank you, Pierre. Keeping nicely to time.
Right, thank you. You can see my slides.
Yes, we can see your slides, Alma.
Perfect. Right, so thank you also, Jean-Luc, for the introduction. So this is the last part, so the last task of the 6.3 task, where we really wanted to look into how can we get to more evidence-based management of drainage systems, and then how can we use the sort of growing data sets that we have, but not everywhere. And we also looked at the English sort of England and Wales CSO data set. So one of the questions we asked here really was, how can we regulate combined sewer overflows transparently? And what are the lessons learned from UK and EU? And it's also of interest, I guess, because it's one of the increased attentions from both the UK Environment Act and the recast Urban Wastewater Treatment Directive. So after a short introduction, I will just have two parts sort of this work. One part of it was presented earlier in the ICUD conference in Delft, but first of all, we wanted to get better overview of how are combined sewer overflows regulated, but how especially is this regulation implemented in different European countries. Then step back again to England and Wales and see what can we learn there from this analysis of the quite widespread, so about 14,000 CSOs that all have event duration monitors on them now in England and Wales. And then we came to quite a lot of discussion, some conclusions, and rather a whole lot more questions, as you do. So I think most of us here will be aware we have quite increasing scrutiny of the combined sewer overflows. We have some changing legislation, which will then need to be translated into updated local regulations. We have, of course, our quite well-known challenges of urban creep, climate change, and aging assets. We have some challenging opportunities. So we've got new sensing and data sharing development, but also public interaction with open data. So transparency and more opening data are becoming quite important. And then what do we actually know about practical implementation of regulation of this? I could not find that much information when we started this task. And then what can we by now learn from this widespread CSO data, the event duration data set that's been collected and opened since 2020 in England and Wales? Could we help identify what makes an area get excessive CSOs? Could we maybe then see what we can learn from that and help us look elsewhere? And then eventually, what type of CSO data could be most useful to collect and release to the public? How may it help with transparency and implementation of regulation? So two parts of this. The first one, we looked over Europe. We didn't really look at data itself, but we just had these 10 regions and we developed questions on try and understand better how implementation of regulation and how the regulations implemented locally and how compliance assessment with local regulations is done and how data is used. And this was also in collaboration actually with the work package 2 of Co-UDlabs. So there's kind of more information there. So we asked a number of local experts to respond and comment. Then second part, we had a good look at the England and Wales data set of annual CSO event duration monitoring data, of which now a few years is available on around 14,000 CSOs. And we analyzed this on different spatial levels using different techniques. So back to the comparison of the 10 countries, because first of all, we really wanted to know how much are actually people using data to assess a CSO compliance. So this does not happen very regularly. Mostly it is sort of model based, or there's data collected but not actually used. And then we also wondered what happens if illegal spills occur. So occasionally there are fines. Sometimes there's nothing, because in some countries there isn't actually a definition, for example, of what constitutes an illegal spill. And in many cases, occasionally, sometimes investigation to the source, for example, of the spill is done, but it's quite difficult to actually track whether any pollution, was it a CSO, was it something else, and where did it come from? We had a big discussion on regulation type, because ideally we look at both what comes out of the sewer system as well as the receiving water impact. So there's emission-based, might be easier to monitor. You say have frequency of spill, or you end up with volume of spill, which is already a lot harder, but it still doesn't tell you about river impact. Or some areas starting to have or have already have receiving water impact-based regulation. That would seem more, or that would be more scientifically sound if you really want to see how are CSOs, for example, harming the receiving water, but it's really complex to implement in practice and therefore doesn't actually happen very often. Or if it does happen, people maybe don't look very well in uncertainties or in all sorts of data. So very complex. So I did actually look in England in the next planning period for Yorkshire, for example, only 2 catchments. So first of all, we look at the emissions and look at maybe any evidence of complaints, for example, or any fish kills or anything. Only after lots of deliberation, only in some areas, people are then really look at impact. So for the next 5 years in Yorkshire, 2 catchments are required to have an impact-based regulation compliance. So impact of intermittent spills, of CSO spills. So this is about £1.7 million. So that's just for the data collection and the simulation to check compliance with the impact-based regulation. So that's 28.8 kilometer river length. This is approximately 1% of the main river length in Yorkshire in a 5-year period. It's similar to the last. So this is going to be hugely changed, because in future, or a very near future, all river impacts will have to be measured upstream and downstream of all the CSOs in England, but won't be able to go into great detail here. But basically you can see this is costly and time consuming. So the regulation is never really perfect, but yet it's necessary, especially as we can see from the England and Wales data set later on. We thought we had quite conservative, rigorous design and regulations in England. However, we turned out to have a lot of CSOs, more than people expected. So regulation is never perfect, yet it's necessary, and we seem to need to really do better. So the emission ones, it's simpler, but doesn't tell the full story. The receiving water impact-based, it's quite complex, costly, and allowing for more interpretations related to compliance. So it allows for quite opaque decision making when you have to make lots of assumptions and they may be not easily understood by people that aren't really detailed into this process. And source tracking, although people like the polluter pays concept, is not necessarily helpful, I think. So what we're really thinking here, how can open data maybe help with regulation and also transparency of where should we start to really look for improvements? So I compare here two experiences. So when we started this, the only area where there was really direct, as far as we were aware, public, easily accessible data was in Brussels through the City to Ocean NGO. They made, so this data was made open by Hydria, and then City to Ocean took it and showed like yearly summaries of amount, duration, number of spill days in the Seine and in the canal. And in England, the Environment Agency through the government made these 14,000 CSOs event duration monitoring public. And then immediately also NGOs like the Rivers Trust, for example, started to make this more easily accessible and opening this up to the public. And then in Bristol, we can see there's some quite positive messages, like, for example, be part of the solution, disconnect your roof. And it shows the number of overflow days as well as the rainfall per year. Sadly, in England, there's also quite a big outcry of the amount of CSOs, but also a lot of really unhelpful press. So here, so in Bristol, the water utility kind of really sat down with the NGO to discuss how to make this data public and how to educate here. In England, it was more like the NGOs just took and ran with it, and the water companies kind of really lost the sort of communication around this data. So a lot of bad press, even to the fact that there's been some newspaper article on workers being harassed in the street, and well, quite a concern about lack of people or lack of skilled people. I mean, we have that in the whole of Europe, but of course this is a big worry, because I might talk informally to people, some of our PhD students, some of them even a bit worried about presenting their results in England when they are sponsored by a water company. So back to the big widespread data set we have. So we looked at different analysis. So the first analysis here was done on local area district level. So these are districts, you can see them here. And I won't really have time in today to work out all the sort of geospatial like statistics that went behind it, but we'll focus on some of the outputs. So here we could see generally some higher spill durations in the west, lower in the southeast, but also really large areas where we couldn't significantly work out whether it was sort of higher or lower spills, and a lot of outliers. So low spills in the west, higher spills in the southeast. So quite a mixed picture when you look at this over the whole country. Then we try to look for correlations between things on this local area scale. So here the number and the duration of spill was averaged over these whole local district areas. And we compared that with total annual rainfall, slope, and GDP. But we can see the correlation, there's some correlation there, as you can see, but it's quite weak. There's a lot of outliers. So we also really wanted to look at this more closely at a smaller scale, because of course here you're combining lots of different systems. So we also wanted to look at individual sewer catchment levels. So sewer catchment is defined as the area that feeds into one treatment plant. And we managed to get all these. So you see all the sponges here are sewer catchments. And then we tried to do a spatial analysis on a smaller scale using self-organizing maps, where we analyzed CSO count and duration per sewer catchments and linked this to a number of geographical as well as sort of socio-economical parameters, and also the rainfall. But this time we took radar rainfall because it's sort of the 1 kilometer, 5 minute resolution. And here you see, for example, in pink, an outline of the sewer catchment, and all the little gray squiggles are lower super output area census area, shapefiles, each containing around 1,500 inhabitants, which is where a lot of our like income and other data is related to. So again, overlapping these is quite tricky. There's a lot of GIS analysis not done by me, by Ichi, who is also on the call later on for something else. But here's like one of the typical outputs. So I'm just presenting one of these pictures. We looked at kind of various different combinations, but again here we thought we now might see clearer correlations, but we actually see less clear correlations. So how to sort of read this map is, for example, here you see the sum of the total duration and the sum of the counted spills within the sewer catchment. So more than one CSO in a sewer catchment. We've summed up here, for example, the total duration, the total spill numbers. So here you can see, as we expected, so basically how these maps work. If we can see two overlapping bright clusters like here and here, data is correlated. This is what we expected because it's total duration and counted spills. What we're interested in is the correlation between these two and all the other potential things. So we looked at population density, steepness, slope, either total rainfall, number of rainfall events above a certain intensity. We looked at rainfall volume, so rainfall times paved area. As you can see, well, you can see lots of colors. We stared a long time at these pictures, but it's actually really hard to find correlations. So you see a little bit here between like total duration and just overall to the yearly rain. But again, when we look at rain volume per catchment, you see some other bright areas that do not seem to cause spills, for example. And again, the clusters, this one's a bit further to the left. They're not actually quite overlapping. So, and also we tried to look at, for example, because there was one paper by other researchers who tried to link this to full flow to treatment and dry weather flow ratio. So you have 3 to 6 times dry weather flow should be your treatment capacity. A number of these treatment plants had lower capacity, but also you cannot quite see. So there's still also areas where there's not much spill, but still maybe lower capacity. It's a bit difficult. And for a large part of the areas, we actually struggle to link the treatment plant clearly to the CSOs. This was not as easy as we hoped, maybe from the open data. So we really struggled to find correlation here. So we think it's lots of other parameters. So the main thing we did find, which I didn't show, is actually about 70% of spills happen at the works, who are, of course, managed to protect the works, not the spill historically. So you use the spills to protect the treatment works. So just an overall conclusion. So although in England we have a lot of data, but it's not collected or widely reported in Europe. We have a lot of local regulations, but the process of this compliance assessment is currently opaque and it doesn't happen regularly due to various difficulties. Now, in an ideal future, this public data will be more transparent. You can hold water utilities to account, but this has to happen very carefully. You have to really carefully check this narrative with your local interest groups and citizens group to not get a lot of unhelpful negativity. And we get a very different experience where this data is made public. So it's still an open question how we can make this data open. And there's an importance of quite clear explanations and positive messaging needed, also for attracting the future workforce, of which we are short. And then in detail from England and Wales, we found relatively weak correlation between CSO spill duration and rainfall seen at larger scales, but not much strong spatial correlations between many other hypothesized what we thought might be explanatory parameters. So there's likely many local factors influencing the occurrence of CSO spill, which is actually what we also find in literature. No simple correlation between observable various and receiving water quality impacts, which making establishing effective regulatory standards really challenging, and discussions are really urgently needed between these citizen groups, what do people actually expect from their water, and what would make people be willing to more pay for solutions and so on, and how can we better make data open to the public. So the details on this is found in deliverable 6.4, which is already on Zenodo, and there's also quite still work ongoing kind of in our spare time at the moment. And some initial parts were presented at ICUD. So here, I think we are in our, oh, I went 1 minute over, sorry, in our question and answers. So do we have any questions?
Well, thank you very much, Alma.
Yes.
Well, I'm not seeing any yet in the chat or the QA. So I've got a question for actually probably for Pierre. I've had past experience of running continuous monitors in rivers, dissolved oxygen, ammonia, and conductivity. It was some years ago. The only one I could really rely on was the conductivity meter. The ammonia and the dissolved oxygen. I was just wondering whether you've got any feel for, has there been, or has anybody got a feel for whether there's been a general improvement in the performance of monitors? I remember back in my day, we had all sorts of issues with them very quickly becoming fouled up in a river situation, and biofilms and the like affecting them. So they require a lot of maintenance. I just wonder if you had a feel for how much maintenance and how are these things really working these days?
Mm-hmm. Yes, thank you for the question. I think I can answer a little bit, and maybe Jean-Luc can add up if he wants. So yes, I think it's very interesting, and I would say that in the sewers compared to rivers, it's even more challenging because rivers are quite clean already, but you still have issues of biofilms and so on. I would say that on our side at EAVAG, the big thing we are trying to develop is contactless technologies for the monitoring of pollutants, because yeah, basically if you want to have a reliable data, it's always better to avoid the contact with the waters. And actually, if we look at the sensors that are state of the art in the sewers, it's mostly sensors that are measuring quantities based on acoustics or on radars. So we are well able to measure flow or to measure a level of the sewers because the sensors are not touching the water. So yeah, in terms of river monitoring, I know that there have been some development made on the use of reflectance spectrophotometry, so the kind of camera-based sensors for the monitoring of turbidity. And yeah, it's also something we are going for in the sewers, but overall, we are all in the same boat, and I think we're all struggling a lot with like putting sensors into waters, having biofilm and other things. Something I can add is that, of course, if you have compressed air cleaning on the measurement windows of your sensors, it can already help a lot. And it's something that we implemented when we installed, for instance, the ESA sensors that I presented before. For the LPICM, so the low power inductive conductimeter, we didn't have any of this. The sensor was just installed in the sewers and was working well. So it's also one of the successes we are sharing in this report. So yeah, these are basically few ideas I can bring in my experience, and I hope I answered the question.
Thank you. You mentioned Jean-Luc. I don't know whether you wanted to add something to that.
Really, no, Pierre was very clear, and yeah, but biofouling and clogging is a key point since decades, and the different technologies proposed by manufacturers are not always systematically satisfactory. Air pressure, I tested myself also some things based on ultrasonic vibrations, but it's never really sufficient. So everything which could help to locate the sensor out of the water would be an interesting progress.
Thanks. And Alma, quite a lot has been done on duration and instances of flow. I know that there's quite a lot of work planned for the UK to actually monitor water quality upstream, downstream. of these discharges and a lot of research. I just wonder if you have some comments on that, as to give people an idea of the scale of what is coming along in the UK.
Yeah, so what's coming along in the UK is slightly, well, worrying, I would say, because there's been such a furore of, which is, I think, why there's a real big lesson learned for everyone in Europe for the recast Urban Wastewater Treatment Directive, when people ask for more transparent data to make sure you get a positive narrative, because essentially the spill data has been open since 2020. And in 2021, after we had the Environment Act, because after Brexit, we needed our own version following the no longer the European legislation. There was then a lot of lobbying. So this Environment Act was a sort of had some idea that we needed more monitoring. Then it was watered down when they realized how costly it was. Then with lobbying, after this data was available, they really lobbied to keep the monitoring upstream and downstream. So the plan now in the UK is to have water quality monitoring upstream and downstream of nearly all of these 14,000 CSO structures. So this will be DO, ammonia, I think a pH, temperature, and maybe conductivity, sort of one parameter still to be specified. And this will be several, within a few 100-meter upstream and downstream of around 14,000 combined sewer overflow structures. So even the one that maybe didn't spill that much with the EDM data, it will be all of them, because the trust has been completely lost in the water companies. Now, this is very costly. So I spoke to people from consultants involved in this. The estimation, because these will be pumped kiosks, so there will be fixed location, which I personally think is a bad idea, because everyone here, or maybe not everyone here, people know a bit about river mixing, know that where the concentration is fully mixed. So to actually work out what proportion in your river came from the CSO, that will vary across the river width and the river length due to dispersion and advection and so on. But they'd go for fixed location monitors, and the monitors, I think the installation is now expected around about £130,000 per monitor or per station. So £260,000 per CSO times 14,000 CSOs. So, and that's just the installation cost. So I think I worked out something like 3 billion, a few billion pounds just for installing the sensor. Now, as Pierre said, these are in the water ammonia sensors. So you have to officially clean them every 2 weeks. I think that's very unlikely to happen. But I mean, it's going to cost billions and billions just to monitor. So let alone working out whether or not, the idea is to then work out, does it come from farland? Does it come from CSOs? Which CSO is? So it's a really inefficient way in my eyes to work out, because we already have the EDM data. Of course, it doesn't tell you if it's 10 big spills in a small river, 10 small spills in a big river, but surely given our rainfall data, we can see, does it spill during dry weather flow, for example. Although I heard from Anglia Water, they are actually also doing that now, started doing that. But basically, because of the way the data was made open and the way the media then vilified the water utilities, there are, of course, install a water but don't flush wet wipes messages on the water utilities. But at the moment, because of this monitoring, our water bills are going up now, I think by about £100 a year, and they will be going up by that for the foreseeable future, even only just to implement this monitoring as well as reduce this number of spills. So anything the water utilities say at the moment in the press, it kind of gets twisted. So for like, they've stolen our money and now we've got to give them even more money and they're still polluting. It's a really horrendous catch-22 situation, I think we are in here. So I don't know that answered your question.
No, I think it does. It's a sort of unusual situation, but as you were saying, it has it is a lesson for other countries to consider.
Yeah, and
I know.
I saw something flash up in the chat and then it gone, that modeling could help answer this, I think, but I can't see that. I just saw it flash and then come back. Somebody asked.
This is from Silvana Hernandez saying modeling could help to avoid so much or so many, I mean, so much instrumentation. So could we use
You
modeling?
could, and it can and it can't. I say modeling, when done well, is wisely. I also have a lot of, because there's, if we look, there's a lot of modeling being used originally, both for design of the solutions like storage tanks or suds or whatever, and also to try and prove whether or not you need them. And I have it from quite a lot of informal chats with consultants. It's really hard. It's really easy to just tweak, say, the amount of paved area in your model or a bit of the runoff coefficient to end up simulating less runoff than you have in reality, or to fit your model. It's not very transparent for decision making, for regulation. There's a big problem, but the same, I guess, data, but it's maybe slightly harder to tweak your data, especially when you put it online near real time. So modeling, yes, clever modeling. I'm sure there's a good place for that. Try and work out. I definitely wouldn't go the way the UK and monitoring the way they plan to monitor the water quality upstream and downstream of every CSO. I personally think it's quite, well, as a researcher, it's going to be quite nice. We're still going to get data. For managing, I think it's very inefficient. Yeah, modeling, our experience with this from informal chat with consultants is that there's a lot of unwritten assumptions and rules that people tweak the model to fit. People tweak the model to fit with the local regulation. That they play the rules using models.
Thank you. I was just wondering, Jean-Luc, is there any final comments you'd like to make? We've got a couple of minutes before the coffee break. And a reminder of what to expect in terms of where information is going to be available from this research package.
Yeah, it was where it is available. I already mentioned it in my slides. So when the final PowerPoint file will be made available for the participants, they can find the information. But I can summarize the 3 work packages with 3 sentences. If you want to improve your sewer operation and management, use the new promising sensors and test them, because we should really make some significant progress in that direction. So the results, the outcomes of task 6.1 about testing of sensors, you can also be inspired by the methodology we use to test the sensors and to rank them and to share also with colleagues, because testing sensor is costly. So we also encourage people to share the data, the information. If each operator tests the sensor and keep the information secret, it's a waste of money, time, and so communication is also a good point. Regarding data, I can only encourage people to try and to play with the UDM software tool, because when we look at the practice, it's far from the recommended best practice in metrology. And globally, the skills of people working in urban drainage are not sufficiently developed in the field of monitoring and data treatment, processing and validation, and uncertainty assessment, and so on. And if we are not stronger enough in these aspects, then the conclusions are based on very weak evidence and on very poor quality data. And it's leading to misunderstanding of the behavior of our system. It can lead to wrong decision in terms of investment and maintenance. And regarding the last part, task 6.3 that Alma developed, it's clear that we have a huge work in front of us to work at a very large spatial scale. And even if modeling was mentioned in one of the questions, modeling cannot be developed without good quality data. So it's important that we start with good quality data, and then modeling can help to extrapolate, to interpret. But if the data quality are not there and not sufficiently obtained or acquired, modeling, I have no hope that they will provide. They cannot invent something from scratch. So again, the data are the key point for urban drainage.
Well, Jean-Luc, Pierre, Alma, thank you very much. We've now got a 10-minute coffee break till 20 past, and we will start session 2 then on the evaluation of assets. So grab yourselves a coffee, answer your emails, and we'll see you again shortly.
Thank you, everyone. My name's Simon Tate from the University of Sheffield, and I want to give you a sort of brief introduction to Joint Research Activity 2, which was about the evaluation of assets and deterioration impacts. So I led the work area, and I just want to give you this short introduction. So the work area was about 3 issues. We were looking at asset inspection, so how we could actually evaluate defects and classify the condition of assets, how we could estimate how deterioration occurs, how we could understand why it occurs, and maybe try and get an insight as to its rate. And then the third aspect of the joint research area looked at the performance of sewer networks and how these could be impacted on the deterioration of particular assets or particular groups of assets. So the pictures on the right give you a sort of start and end of where we've been over the last 4 years. So the first pictures, the first question we asked is we obtained some videos from Japan and some European videos, and the quality seemed to be very variable, and the ways in which both countries evaluated their assets and looked for defects was very different as well. And we did ask the question, was there somewhere better way to do this? The final presentation you'll see this morning from this work area will be a way in which people can monitor system performance or model system performance based on an estimation of where defects actually are. So Ichiwu will talk about that in about 20 minutes. So we did some work looking at automatic defect identification. So one of the things that we did first, if you look at the left-hand side, is we actually looked at the condition classification coding that we have in Europe now, and they're very complex with lots of subclasses. And we actually tried to look at which classes, types of defect actually impacted in system performance. And then we took the existing classification and simplified it into key defects. We then looked at a method called deep learning for images to see if we could classify images automatically. And if you classified images based on these more limited classifications, you had quite successful identification or automatic identification that you can see on the right-hand side. We also took some historical information, and we took this information from asset inventories, pipe failures, and also rainfall data, and we used a technique for unstructured data called self-organizing maps. We used this data, this technique to identify key aspects, key input variables, and then we used some supervised machine learning as a random forest type classifier to get the risk of where you're likely to find defects within a system. So you can come up with maps like these, which sort of indicate from historical data where you're more likely to see a defect within your network, and therefore use this information to provide you with more targeted defect identification. So you can see on the right-hand side for this network, from the historical data that we obtained, that probably the top 16% of assets are where the failure probability or the likelihood of meeting a major failure is high. So this led us to think about just how do assets deteriorate. So we came up with this plot on the left, so you can see the sort of orange-blue lines. So, the traditional method of deterioration was a sort of corrosion type process, where you gradually deteriorate and with small jumps, but it's almost a sort of linear type deterioration. But when we looked at some asset records, then you probably got something that was close to orange. So quite a slow deterioration, and then a more rapid deterioration in terms of the condition of the asset. But you also got pathways such as B and C, where B is that you degraded very quickly to a low asset condition, and C that you had large steps, but you had a large step in which the asset deteriorated, and then it gradually deteriorated again. Now, these sorts of concepts are important because you measure asset condition at unique points in time, and it's important to be able to predict whether these assets are stable or whether they will suffer sudden deterioration. We saw that there was a gap in actually measuring deterioration in the laboratory, so we devised more accurate ways than just images of defects. So you can see here a 4-camera inspection system that aimed to not only identify the defect, but also the size of the defect itself. And from that size, you could see a rate of deterioration. So you can see the sort of 4-camera system in the pipe itself, in the concrete pipe, and the type of information it gives you, as you can see on the right-hand side. You've got two different pipes there in the color plot, and you can see that the joint down the middle. And in this concrete pipe, the pipe was loaded, it was buried, loaded through the soil, and effectively you could see that the pipe slowly opening. So the line plot on the right-hand side, you can see the joint in the middle, and you can see that the two pipes don't quite match up, and this joint has been exercised to open the joint itself. The reason that we wanted to develop more stronger, more quantitative measures was that we wanted to be able to transfer measurement capabilities between laboratories, and we did this within the project. So we now have 2 laboratories in the project that use this sort of measurement technology, and we wanted to make sure that any sort of laboratory testing of deterioration was transferable between different laboratory environments to meet this gap of assets or measuring assets as they slowly degraded. Another key thing of trying to make comparability between laboratories is to ensure that the assets that you have in the laboratory that you're studying are actually representative of the real world. And you can see on the photographs on the left-hand side, one's a sort of crack and one's an intrusion, and these reflect what's seen in reality. And this was work done at IKT in Germany, where common laboratory defects were classified with help from end users, so that we can be assured that if we do carry out laboratory deterioration tests, that they are representative of reality. So Thomas Brueggemann from IKT will talk about this in the next presentation. We move on to the third aspect of the work, and that was the impact of defects on system performance. Ichi-Wu will talk about this in the final presentation of the session. So you can see 2 figures here. The first figure is from quite a small sewer network that was modelled with individual defects. And the important part here with the colour plot is the red dots where you have a severe impact. So you have a defect placed in a pipe, and then we search the various nodes in the network that are impacted by that defect. So you can see that most of the impact in this small network, only about 200 pipes, was quite close. So you have the 45-degree line down the middle of the plot. But you can see that you've nodes on the horizontal axis and conduits in the vertical axis, you can see that there are quite a number of red dots which indicate that the defect has quite a remote impact in the system itself. And then if you look on the right side, it's a much larger network, about 4,000 pipes. You can see that the colours here, the sort of orange colours, indicate pipes with a defect which cause additional flooding. Now, it may be that the additional flooding is local to the defect, but there's also a considerable number that are quite far away from that local defect. So Ichiwu will talk about this in a bit more detail. So let's have a look at the conclusions of JRA2. We had sort of 3 target areas. We wanted to look at inspection technologies and to look at opportunities to improve them. We also wanted to carry out laboratory experiments and to examine deterioration mechanisms. And we also wanted to develop modelling approaches to look at the impact from individual pipe defects and whole system performance. So I think we accomplished all 3 of those. So certainly we explored image-based methods to automate defect identification, and I think crucial aspect there was looking for more simplified defect codes. Now, we had defect codes that fell into 8 groups. The Japanese have a defect coding system that looks at 5 groups. So our argument here, or what we got from the measurements, that you needed more physically relevant defect classification. So looking at groups that would have an impact on system performance. Looking at deterioration of defects is quite new. Most times we just have one snapshot of a defect. Some CCTV data has been redone, maybe several years after the first observations, but that's quite rare. And what we wanted to do in the laboratory was to stress pipes by loading them to look at, in our case, infiltration. So we did some work to make sure that the defects we used in the lab were transferable and representative. And then we also had a preliminary study on infiltration and exfiltration that Thomas will talk about. In terms of the modelling studies, we started small, looking at very small networks, and then moved to a much more representative 4,000 pipe network. And you started to see interesting patterns. It was clear that individual pipe defects had an impact on the whole system performance, both in terms of flood risk and overflow volume. And as we moved to larger and larger networks, the computational load of the analysis became higher and higher. So hopefully that's given you an overview of the 4 years work in JRA2. And you'll hear 2 presentations now from Thomas Brueggemann from IKT and Ichiwu from the University of Sheffield, who will look at the last 2 bullet points in a bit more detail and present some results to you. Okay, thank you very much.
Yeah, thank you, Simon. I will share my screen now. Can everybody see my presentation?
That's not the full screen yet. It's your presenter screen.
Now or not? I tried to do it again. I don't know why it is not working.
You might do. No, it's still not the full one. You might need to stop sharing and start sharing again and use the the window. And then
or just sharing the window, or what are you talking
Yeah,
about?
I'm afraid it's still showing the not showing your full screen. If you like, I can put your full screen up. You just, yeah.
Can you see now the full screen or not?
No.
Oh, okay. Maybe you can put my presentation on. I don't know why it is not working.
Okay, can you see that now?
Yeah, I can see it. Okay.
Okay.
Yeah, thank you very much for this introduction, Simon. Yeah, my presentation is about the topic damage scenarios in the sewer system. And yeah, this topic was also considered within Co-UDlabs. Next slide, please. Yeah, on the first slide, you can see the typical defects in the sewer system. This is an evaluation of the German Water Association DWA of the year 2020 for Germany. But in my opinion, we can assume that this situation is similar in other European countries. There are three most represented typical defects, which is the crack formation. You can see it with 25.7%. With its impact on stability and excellent infiltration. Then the protruding or defect lateral connection, which is caused in the most cases already during installation, non-conform installation. And the pipe connection itself, it is with 18.6%. Sometimes caused by installation or also caused by settlements. These three types of defects have in common that they could lead to exfiltration and infiltration. So what could be of interest in the lab? What could be the scientific question to be investigated at lab? So here are some examples. For example, the exit and infiltration behavior. We had a look within Co-UDlabs on the exfiltration. But also failure mechanism could be the topic in at lab, looking on processes regarding stability and tightness, regarding typical defects. Lifespan, service life could be a question. Also the influence on operation, the influence of different kind of damages on operation. I'm thinking there of high pressure cleaning. This could maybe widen or a defect or something like that. And then, of course, the performance of different kind of renovation procedures could be also a topic, and materials. So when you're simulating defects at lab, you could also have a look on the performance of renovation procedures, how to renovate these defects. But the overall question is for lab and also for within the Co-UDlabs project, this question was discussed: how to create typical defects at lab. Next slide, please. When you want to create defects, typical defects at lab, what to have in mind? First of all, the scientific question should be clearly defined to select appropriate defect. That should be clear. And you should use a defect at lab with its relevance in terms of its frequency, location, and occurrence in reality. I think that makes also sense. The defect at lab should be based on characteristics of the corresponding defect in reality. And very important is also to ensure the reproducibility of the defect at lab. So yet, for example, you should use, when you're creating defects at lab, a template stencil, or the same tools should be used when you are producing them, and the same stuff should be used. A detailed, traceable, and transparent documentation of each step in the production of defects lab should be made. Beginning with the process of decision making, choosing, for example, a relevant defect. up to the planning and up to installation. This is needed for justification and argumentation following the fair data principles, I would say. And you could say we could recommend that network operators, municipalities, and water companies should be involved in decision making to ensure practical issues. For example, at IKT, we're working close together with municipalities, which are part of a project steering group, deciding how to which damages or defects are relevant, and so on. Next slide, please. Now you can see some typical examples for defects in reality, and yeah, also examples or ideas how to create them at lab. We prepared or developed within Co-UDlabs a defect catalog about this, about these defects and how to create them, or examples how to create them at lab. First of all, you can see here a fissure or crack. This is typical also in reality. And the creation app lab you can see below, created by a saw, for example, with a saw, and different kind of cracks are simulated here. This catalog is mainly based on experience of IKT. We made 20 years ago the first projects about comparing rehabilitation systems and inspection systems, and therefore we created in different kind of projects, we created also different kind of defects. Next slide, please. Next example for simulating the defect is a break or collapse. You can see it was also created with a saw at a lab at IKT. Also different kind of defects you can create there regarding this collapse. Next slide, please. Next example is the displaced joint. It's also coded within this standard you can find here. I think it's a Euro standard. Here you can see it. It's a Euro standard. The displaced joint was also created in the past within some projects of IKT. Next slide, please. One of the interesting defects is also the infiltration, because you can't see it, not really with the defect with CCTV. Sometimes you can see the defect, can't see the defect because, for example, the ceiling is damaged. When the ceiling is damaged, but you can see infiltration when the sewer system is below the groundwater level. In the past, we also did some research at IKT simulating these defects, the special kind of defects in our large testing facility, which with soil and also with simulating the groundwater level, just to see if water infiltrates, and also to see how the rehabilitation companies could cope with this problem. This displaced joint and infiltration, also exfiltration, was put together within Co-UDlabs just to create a special defect damaged sealing at the pipe joints and combining it with the displaced joint. Next slide, please. The question was, or the background was, what I already said, that the pipe joint displacement identified by CCTV, but you are not able to see any exfiltration or exfiltration risk for this kind of defect. As you can see, this defect pipe connection belongs to the three main defects in this evaluation of the DWA. So therefore, we created a test setup at IKT and also a test setup at University of Sheffield at iCare. And first of all, we build up a test setup at IKT. Next slide, please. I'd like to explain now. We did some, put some two pipes together and without surrounding soil and measuring water exfiltration at this test setup at IKT. Under changing conditions. For example, we changed the pipe material. We did these tests with concrete pipes, with clay pipes, and also with plastic pipes. And changing of conditions during these investigations was also varying angles at pipe joints. That was interesting for us to see if there is exfiltration and how much water will come out, and with and without damaged sealing. That was also the question of these tests, to see if there is a difference when you damage the sealing, if more water comes out. Then these tests at University of Sheffield were done, nearly the same tests with surrounding soil, the measuring the water exfiltration rate also under conditions like using pipe material concrete, using surrounding soil. That was here now the other situation, and a load was put on the pipe connection to create pipe joint displacement. A load was put on with a cylinder there. Next slide, please. But also part of this joint research activities, and Simon already mentioned it, was the challenge for University of Sheffield to develop and demonstrate a new displace measurement system for in-pipe joints. It's called digital image correlation, based on the analysis of changes between image taken before and after the formation of a target surface of its spatial and optic characteristics. So this system was developed at University of Sheffield and then picked up and also bring to IKT. And we demonstrated at our test setup there at IKT. Next slide, please. What are the conclusions of these investigations at University of Sheffield and at IKT? First of all, we have to say that there's a high level of water tightness for a wide range of pipe articulation for clay and concrete and plastics. But there's a difference between clay and concrete pipes and plastic pipes, because clay and concrete is very stiff material. So stiff pipe sections continue to deform the joint seals as articulated to higher angles. Higher exfiltration rate than PVC plastic was observed. For plastic, I can say that there was for an articulation angle more than 2 degrees. Pipe itself deformed. The joint geometry remained similar. Exfiltration rate reduced to negligible values. I think that's a very interesting observation. And you can see on the right-hand side the table of the results of this measurement. Also the measurement with this new system developed by University of Sheffield. And you can see this observation here in this table of the results of measurement. Next slide, please. The third point is that the functioning and effectiveness of the low-cost DIC measurement system developed by University of Sheffield could be demonstrated. The fourth point is the bedding material surrounding did not significantly impact the exfiltration from pipe joints. That was the observation of the tests at University of Sheffield at ICARE. And the in-air exfiltration tests we did at IKT could be used to estimate exfiltration rates from articulated pipes. And this was observed with and without damaged seals at joints. If you like to get more information and more detailed information of our research within work package 7, you can find the reports on our internet page from Co-UDlabs for how to create defects and also for the topic exfiltration of pipe joints displacement. Yeah, thank you very much.
Thank you, Thomas. I'll stop the sharing and hand over to Yiji.
Okay. Everyone see the PowerPoint?
It's not appeared just yet.
Okay.
Yes. I think your camera, yep, that's fine. Okay, over to you.
Okay, good. As briefly introduced by Simon, this piece of work I've done is looking at the defects and deterioration of assets in a sewage system and how that will affect the hydraulic performance of the whole network. So the vulnerability of the assets to the performance caused by the defects examined by analyzing the location and the volume of flooding caused by the deteriorated pipe. So we have made all the analysis in Sweden, and we've performed a case study with the sewer network at the Sheffield, Switzerland, which stands on the right bank of the River Rhine. And on the left-hand side, this is a overlook of the whole system in Sweden. We've tested with two types of defects, which one is siltation and the other one is root intrusion. And the on the map, we have two rainfall stations. One is Herberlingen, which is located at the main city area, and where another one is Hamato, which is on the left-hand side, which is the remote town linked to the main city. Okay. Sorry. Yeah. And the model is calibrated with the level and flow monitor, which has been placed in the location mapped on the map. So the sensors have been recorded for a year-ish data, and we've tested in stream and calibrated models. So the model result is close enough to the measured data. We've also looked at the effect of defects on the overflows later. So the two types of defects simulated in this study are siltation and root intrusion, and siltation is simulated such that the bottom half of the pipe is filled. And the root intrusion is simulated such that the diameter of the pipe is reduced. So the top bit of the pipe is shadowed, and we've ensured the available capacity of the pipe, which is the remaining capacity, is the same for both defects. So they are more comparable. And we have tested with 3 rainfall scenarios. So we've chosen a real-time rainfall event, which lasts 2.5 hours. Choosing it because it's short duration, which helps us as to reduce the simulation time required. And this particular event also have a quite high rainfall intensity. We simulate with 100% of which is the original rainfall event, and then we reduce it to 50% of the intensity and then 30%. So here's outline of the methodology. So we've chosen the rainfall events and deterioration level we want to start with, and then we run the simulation, assuming all the assets are in acceptable condition to establish the baseline performance of the model. And we deteriorate one pipe at a time by changing its characteristics, the parameters, to mimic the loss of serviceability. After we run the simulation, we extract the results and compare the flooding volumes with the baseline. And if that pipe caused additional flooding, it is a critical pipe, and if it's not critical at this rainfall level. We've just run it for all the pipes, and after all pipes are simulated, we look at whether we have critical pipes under that particular rainfall level, and if we still have pipes that are critical, then we reduce the rainfall intensity and run over this simulation again until there's no critical pipe left. So to do this, this is for us to see which pipes are critical and which rainfall level is the critical threshold level that would cause a pipe to fail. Just a brief idea of how long that simulation would take. So for one pipe and for one rainfall event, it takes 6 minutes to run the simulation. And if you run the simulation for all the pipes in the network, which is around 4,400, it takes much more times. So that's why we introduced the parallel programming, so we can run multiple simulations at once. And with the PC that can run 24 simulations at a time, it takes roughly 36 hours, 1.5 days to run it. So it's quite computationally demanding. And that's why we choose a relatively shorter rainfall event in this case. So here is the results of the simulations. So the additional flood loss is the amount of flooding that minus what's already been flooded in the baseline scenario. And the color map shows the amount of additional flooding on the map. And for easy comparison, that's being converted as a percentage increase rather than absolute value. So it's we can compare the two different defects and the effect of them. So see a dark orange line on the map, that means when that particular pipe is deteriorated, it caused a large amount of additional flooding in the whole system. And in addition to that, we also evaluated the radius of the effect of the defect. So we look at the distance of the nodes that's flooded when the pipe is blocked, and we'll calculate. It is mapped on. Sorry. Sorry. Anyway, so the distance of the flooded nodes is presented on a map as the thickness of the line. So if we see a thicker line on the map, that means the nodes are flooded when the pipe's blocked is further away from the pipe. So what we see here is with the 100% rainfall event, the distribution of the criticality of the pipe is quite, I say, even across the whole network, except the line which connecting the Hamilton village to the main city, as because there's only one pipeline going through that village to the city. So once one of the pipe is blocked, it has a big effect on the whole system. And it might not be very clear, but then the line thickness of the outer edge of the city is slightly thicker than the middle of the city, but in general, they are quite similar. So say on the 100% rainfall level, the flooding is quite localized. That's probably because the system has already reached its capacity, so any additional flooding has caused by the defects is going to be reflected in the local nodes very soon, very quickly. And compare between these two different defects, although the pattern, I mean, the ones, the most vulnerable ones are quite similar. They are all same. They are all at the line with connecting the village to the main city, and there's also a few bits in the middle of the city. Although they differ from one to the other, but general pattern is quite similar. And then we've taken the ones that has caused additional flooding in the last stage, and we reduce the rainfall level to 50% of the original intensity. Then we see more clear pattern where we have the pipes that's on the top right-hand side and close to the edge of the city as being more critical, and the one that's in the middle of the city, which probably collect most of the water from other parts of the city that's being critical. And the distance of the defects to the flooding is much more clear here as well. So the ones on the right-hand side, they are less localized because the lines are much thicker. So which means when they are blocked, they have their effect of the system probably is more further away, while the ones on the left-hand side, they are more localized. Sorry, okay. And then we further reduce the rainfall level to 30% with the ones that's flooded in the last scenario. We only have a few pipes left in the top right corner, as well as the left-hand side. So those ones will be the ones that's going to flood in the low rainfall events. Probably, as a manager, will consider to maintain them first because they could fail very quickly. So there's a summary of the results we've just showed earlier with different rainfall volumes. The number of pipes that caused additional flooding is going to decrease. With 100%, almost all the pipes is going to cause additional flooding, which has a defect. But when it's reduced to 50%, only less than half of them are going to cause flooding. And when it's down to 30%, there's only a few of them. And when it's reached 20%, none of the pipes has flooded. And for both of the defects, the number of pipe caused additional flooding is very similar, although the one with top intrusion is less than the siltation scenario. It's probably because the siltation also elevated the inward level of the pipe that could reduce the hydraulic capacities in the pipes and change the hydraulics in the pipes. So we've also looked at the overflows under various rainfall patterns and with the siltation scenario in this case. So there's 3 events we've looked at. Event one is the one with high rainfall volume and also with a relatively long duration. And event 3 is actually the one we've used in the previous study, and it has a shorter duration, but also the intensity is also high. And we also tested event 6, which has been adjusted such that the total volume is the same as event 3, but they have a longer duration. So we're just comparing with how the rainfall pattern are going to have effect on the overflows, given that we have the same amount of rainfall. So the graph down there shows roughly the rainfall patterns in these 3 cases. And we have 9 overflow ZSOs here in the city. So with the event 1, where we have a long duration and high intensity, 8 of them has overflows within the simulation. And for the next event, which has a shorter duration, only 3 of them has overflow. And for the third event, which has a low intensity, it has no overflows. And then if we look at these 3 overflows location, which has readings for both event 1 and event 3, the color shows the percentage change of the overflows compared to the original baseline. So the color map ranges from green to red, and green means negative, which means there's actually a reduction in the overflow, and yellow means there's no difference, and red means there's an increase in the overflow volume. So these 2 events, under these 2 events, for event 1, most of the pipes basically doesn't change or slightly increase the overflows, where for event 3, most of them actually decrease overflows. If you see the scatter plot of the distance to the percentage change of overflows, we can see similar patterns in the 2 events. The ones that are closer to the overflow location is having more effect to the amount of overflows when it's blocked. And for this particular overflows, we have a more mixed results. So for event 1, most of them decreases the overflow, and for event 2, it's this increase and mixed increase and decrease. And similarly, the scatter plot shows similar patterns of the pipes that's going to have the effect to the overflow. And for this overflow, which is quite remote to the main city area, which is located just next to the exit of the village, it has very minimal or recess, basically their effect to the remaining of the network. So only the ones that's very close to that overflows when it has blocked is going to increase the overflow slightly. But if any pipe changes blocked in the rest of the network, it doesn't change the overflow volume. So we've also looked at the other overflows, which only had a reading for event 1. We have different results for different overflow locations. Some of them is going to decrease when pipes are blocked, some has no impact, and some going to increase overflows. So if the main goal for the network managers is to reduce the overflows in the system. So when the pipe are blocked, or if you put gate on the pipe, it might actually help the overflows and vice versa. So here's a summary of the overflows results we've had a look at in the previous slides. So I've listed all the pipes as which ones has increased overflows when it has a defect, and which has decreased overflows has an effect. It's shown here, like some of them, for example, the first one, and with event 1, 92% has an increase in overflows, but only 8% had a decrease. So majority of them, when it has a blockage, actually increase the overflows. But for the second overflows, you can see that the result is reversed. So when it's blocked, it actually decreases overflows. So which is that basically means well, if you look at the overflows, it's quite important to look at the local local network setups, because that will has a big effect on the how the pipe is going to affect overflows in general. So, in conclusion, the flood risk pattern can vary for different defect types and different rainfall scenarios. And for the case study we had, the analysis shows that the pipe near the outfalls and northeast part of the cities are more prone to floodings when it has defects, which says in these areas probably will be the priorities when people are going to do maintenance jobs. And the defects in pipes can lead to both positive and negative effects on the system overflows, and the extent of these effects are influenced by the pipe location and the characteristics of the network. That's everything.
Thank you. And I just looking at no questions in the chat yet, so please do add your questions to the chat. But a very interesting observation. This is perhaps one for Simon and for you, Yiji. We talk a lot about with preventing flooding in surface waters. There's a lot of natural flood management now, people introducing leaky dams and even reintroducing the European beaver to places to hold water back. I hadn't really quite appreciated until I saw this, that actually defects in pipes that reduce their diameter could actually have a positive effect in some places on flooding from sewers. And it ties back to other research that goes on with holding water back in sewer systems using automatic gates and things like that. I'm just wondering, Simon, have you got some evidence that this could work in sewers now?
Ichi, do you want to answer that, or?
From the modeling, yes. It is actually showing that if you put holding water back, actually you're using the capacity in the existing system. So it actually helps the overflows in general in some cases. But I guess it's more dependent on how the network is set up and where the location of the overflow is.
I suppose I was thinking in some cases repairing the damage might actually result in more flooding.
It also depends on the rainfall as well, but yeah, it makes sense. It's a very distributed network, and retaining some water on parts of the network helps others.
It's just a curious observation I just made.
But it does show that you need to have a network model to understand these things, Ian. That you can't just sort of say, well, we'll deal with the defect close to the flooding location. You know, somewhere defects quite far away can affect both flood risk and overflows.
So that is very interesting. Again, just looking for questions from the participants. Do please post them if you want to. The issue as well, Thomas, the difference between the plastic pipe and the rigid pipe in terms of the infiltration as the joints were flexed is I'm just wondering to what extent that sort of does happen in reality, and if this is a useful finding for municipalities.
Yeah, I think so, because they can estimate if they see some kind of angles there or displacement, they can estimate the exfiltration rate. So if there is, of course, if there is a groundwater level, you can see infiltration through these displacements, but not exfiltration when there is no groundwater there. So if there will be more research in the future, you can make some kind of estimation for every kind of defect regarding displacement to see to get information about the exfiltration rate then.
I think people often forget, there's a lot of focus on infiltration. People often forget that there is exfiltration as well from sewers, and particularly where you have shallow aquifers, pollution from sewers is quite an issue. So, Simon, so looking to the future, we've done this on a couple of trial sites, locations. This methodology that's been developed here is readily applicable to other locations?
The numerical modeling.
Yes.
Yes, the methodology's applicable, but the computational resource you need is really quite high, Ian. It's not something that I think even a very large consultancy may have the computational resource, but I suspect most engineering consultancies wouldn't.
Yes.
So,
there is
I mean, Ichi, do you want to give some, examples of the computational resource, just to give an idea of the size?
Yeah, I think two things. One is the computational time, another is the storage we needed. So for us, because we used laptops for with 24 cores, so we can run 24 simulation at a time. And that significantly reduced the time we needed. Otherwise, this particular simulation we've run for one scenario probably will need a month time, because it cost a day and a half without that. And so another thing is the storage. It's like one simulation results, and the output file will probably like 100, 200 megabytes. But if you want to run longer durations, say a month or a year, that probably take a few gigabytes. And if you're thinking of doing that for the whole network, for every pipe, that was just a huge demanding of the storage and stuff.
We've got one question here in the chat from Silva Hernandez, who's saying, with which part of the sewer network should be included in the inspection in order to be enough for a correct flood simulation? 25%, more, 100%? How much of your network should you try to include?
So I think for us, we have the detailed sewer network, like the locations, the lengths, the gradient, all that is definitely needed. Obviously, there's another question of monitoring the assets and conditions and stuff. I would say like at least to put a few monitors in several locations of the network in order to actually calibrate the model. But it's hard to say how many percentage will actually is definitely required. Let's say. Sorry.
I'll give an opinion. I
Yeah.
think you need almost all the sewer network in, because some of the impacts can be many hundreds of meters away from the defect, as Ichi showed. So you really can't exclude parts of the networks as not having an impact, because some of the impacts are really quite remote.
Yeah. And there's another observation here by Johan Van Assel, who says, I think you should also bear in mind that in reality, defects can occur in a clustered way, and their total impact may again be different from the pictures you've shown here.
Yes, I think so. But this the second step. The first step is to have a look on the defect itself and to get information about it. For example, to get information about exfiltration rate of this defect. And then the second step is to think about clustering these defects. Maybe Sam, you want to add something?
Yeah, I would agree with it. Defects are clustered, but as Ichi just said, the computational resource to look at whole networks with individual defects is really quite considerable. We are thinking at the moment to see if we can look at groups of defects, and we can do it for a few defects, if that makes sense. But one of the issues that we've come across is that the distance between defect and impact can be hundreds of meters. So the assumption that you can have a look at a small group of defects and look at the impact, then yes.
Okay. Well, thank you very much, all three of you, for your contributions to that session. I think it's been quite thought-provoking in terms of how we take this forward, and fits in very nicely after the first session that we've heard about the use of sensors. And we are now going to have another break of 10 minutes for coffee before we come back for session 3. So we'll see you again in a few minutes. Okay, welcome back. And Juan, would you like to take the screen and put your slides up?
Yes, I can do it now. I hope everything is working now.
Yep, can see that perfectly. So over to you. I know you've got a lot of quite nice videos to show, and but quite a long presentation, so off you go.
We can do it. Okay, so hello everyone. I'm Juan Naves. I'm working on the University of A Coruña, and I was working these last 4 years in the Co-UDlabs project. So it's a pleasure for me to present you the main results of this Work Package 8.
Could I just check with Ian and Ovia if this session is being recorded?
Okay.
I can't see that it's being recorded, but I'm assuming they will set the recording going. Okay.
I think
Right.
so.
Yep.
Okay, thanks, Ian. And so this work is the work of 7 partners of the project, and almost 30 researchers that are involved in these activities, and at least as author of the deliverables that we have. The main activities, as you will see, this work packages is more like a mix of several activities in the field of urban drainage, and my intention is to give a general overview of all of them, and then if you want to go further in one of them, just ask us, or I will leave some links on these slides. So the main activities are related with the assessing of innovative technologies and methodologies on urban drainage infrastructure, the investigation of plastic transport in urban environments. Also, we have assessed methodologies for the characterization of permeable pavements, its long-term performance, and some work on the hydrodynamic design for stormwater detention ponds, and the use of designer soils for SUDS, for sustainable urban drainage systems. We are going to have some specific presentation by James Sacksmith related with the hydraulic energy losses and transport contaminants during seaward to surface flow interactions and flooding network surcharge events. And finally, we are going to have one presentation by Joao Letao from EABAG on the long-term performance of blue-green infrastructure, in specifically the influence of leaf litter and sun on the water balance. So starting by the new techniques that we have assessed, this is the new techniques to build up a high resolution geometry of urban drainage infrastructure. We have used this big facility, this 1:1 scale, 100 square meters size of one surface with two across of 2 streets and roof building, and then a seaward network below this surface. For taking the digital terrain model, we have used a LiDAR and real sense depth camera. These sensors are not cheap, but are also not expensive. It's less than 400, 500 euros. And we have also assessed the use of photogrammetry technique with the software, with the structure from motion technique. You can see here how is the detail of our digital terrain models that we are obtaining with these devices. And our purpose, or the thing that we did, is to take one 3D model for each of the techniques, and for the surface and also for roofs. And we are currently analyzing how this topography, or the accuracy of this topography, is affecting to hydraulic results, for example, in the flow that is entering to the inlets. Due to the very shallow flows and the impervious nature of urban catchments, the influence or the sensitivity of the results to these topographies is quite high, and we are trying to quantify. If you want to know more about this, is explained in detail in the deliverable 8.1 of the project. And also I wanted to leave here some links to the data sets, and also some related publication on the numerical model that we are using, and this comparison between the topographies. We have also assessed the use of imaging velocimetry techniques for urban drainage application. With cameras, we record the surface flow on the same street, in this case, and through the tracking of these particles, and using software like OpenPIV, for example, we can determine and estimate some velocity field vectors that we can find of the surface velocity of the water on the urban surface. Why this is interesting? The first part is to validate and calibrate numerical models. It's interesting data to know more about the performing of these models, and also to understand all other associated processes, like the sediment wash off on the street during rain events. For example, this is a hydraulic characterization of one part of the model that we have used to understand some tests that we perform of the wash off of some sediments during a transnational access that we have here in La Coruña. And also we are using this, we have used this technique for the obtaining some data on the surface velocity in the retention pond or the sediment retention tank in Aalborg University, in a collaboration that was performed in the frame of the deliverable 8.4, if you want to know more about this. 8.4. I leave also here some links on the deliverables, data sets, and also some publication that we perform on this topic. The last device is the use of temperature sensors or temperature measurements for the estimation of sediment depths. This work is developed by Manuel Regueiro in his postdoc, and was a collaborative action with University of Coruña, EABA, Deltares, and also INSA Lyon and Coventry University. The idea of this sensor is to place a temperature sensor at different levels in a galley pot, for example, and to measure the temperature. The performing is, or the basis is that in dry weather, you have the same temperature in the temperature sensors that are in the water and also inside of the sediment layer. And when we have a rain event and cold storm water comes to the galley-pot, the temperature of the water is reduced quickly, but the temperature of the sensors that is inside of the layers is reducing in a attenuated way. So studying this different behavior between the temperatures in the water and inside of the sediment layer, and applying the heat transfer equation, Manu or we can estimate to estimate the depth of the sediment layer that we have on the galley-pot. The technique was also used on sewers or exploring the use in sewers with the annular flume of this facility of the Coventry University, and in this case, instead of a flux of cold water, the principle is to use the daily pattern of temperatures that we can find in sewers. If you want to know more about this technique, you can ask Manuel Regueiro or consult their recent publication on this topic. The plastic transport on urban environments was also a research line included in this work package 8. As you see here, this is in this study we have studied the incipient motion of macroplastic on urban environments. This was a work that was performed in the frame of a transnational access, but also is related with the work that we was doing in this joint research activity, and was a collaborative work with the Karlsruhe Institute of Technology. Another cool and interesting experiment is this experimental campaign of the time of retention of the macroplastic inside of the gallipots with different kinds of macroplastic, as this paper of chocolate or some bottle taps. They do statistical analysis to understand how is the behavior of these macroplastics inside the gallipots. And also in this research line, also INSA Lyon also investigate the interceptions of microplastic through Stirling basin that you see here. The name is the DSM flux that was developed recently by them and designed to monitor the TCO discharges and to trap part of the particulate pollutants that come with these TCOs. With the Co-UDlabs project, they have developed a methodology to measure the trap efficiency of macroplastics of this device. They developed this methodology and also perform some experiments where you are saying that the trap rate of these microplastics was around the 25% of the particles. If you are interested in this experiment, you can check our deliverable 8.2. And regarding the permeable payments, at the beginning of the project, we have observed that there is a wide quantity of variability in the methodology and methods that are being used to characterize the initial permittivity and also the long-term performance or hydraulic performance of this kind of solution. So our purpose here was to review that methodologies and assess them using different rainfall simulator, as you see here. The first one is in the IKT rainfall simulator, and the second is in the University of A Coruña. Both has 1 square meter. And in this rainfall simulator, we have tested different pavement topology, like this porous asphalt, interlocking permeable pavements. We have used, as you see here, this different sediment to produce that or to simulate that clogging. For example, this is a millisil, there is a quartz sand, very fine one, that is in the German standard. And we have also used microplastic as tire dust, and also real sediment that we collect from the parking in the campus here in A Coruña. This real sediment also was used with different granulometry, and the idea is to assess the influence or the performance of all of this methodology, of all of these variables that we have in this test, towards or to contribute with some recommendation towards standard methods to make the experiment that we are doing comparable between one and the others. And with this result, we have also do some experimental work on upscaling these results. And we have used a porous asphalt in a 1:1 scale 36 square meter facility and distributing sediments in different steps to simulate the clogging and measuring the inflow of the water that comes from the inside of the asphalt, and measuring water levels inside of the asphalt during rain events, and also some punctual permeability on the asphalt to track that clogging. If you want to know more about these studies, you can go to the deliverable 8.2, some data set that we have already published in the Zenodo, in the page in the community of the Co-UDlabs project, and also some related publication that I leave here. The University of Aalborg lead this investigation that on the hydrodynamic design for stormwater detention ponds, optimized for a cost-efficient maintenance. Detention ponds attenuate high flows during the rain events and allow a more controlled release of stormwater. The stormwater detention ponds serve also as a mechanism for trapping a significant portion of organic and inorganic particulates present in this stormwater. In this work, the flow and sediment load coming into a 5 meters long, 20 meters pond from a small urban drainage catchment based close to Aalborg. And you can see here some plots on rain and inflow data for one of the several events they characterized, and also total suspended solid concentration taken from the inlet of the tank that is taken with these outro samplers. They also characterize the samples of sediment that are retained on the retention tank, and these, together with 3D numerical simulations, pretend to help in the development of cost-efficient maintenance strategies and also the optimization of the hydrodynamics of the detention pond. You can find more about this in the deliverable 8.4. In another activity carried out in the frame of this work package 8, INSA Lyon has led a comparability analysis between natural soil and Harroton substrate. That is, Harroton is made by a company in Germany. And this comparison was performed regarding physical and hydrodynamic characteristics, and also continuous monitoring of flow, conductivity and turbidity, and sampling and chemical analysis of dissolved organic carbon and heavy metals before and after the substrates. The results are promising for Harroton substrate, and you can find further information and interesting results related with this in the deliverable 8.5. I have no time to go deeper on the results. And finally, the University of Aalborg has been developing a preliminary version of a user-friendly model for design of a filter soil under a basin for local area infiltration or soil-based sustainable urban drainage systems. The developed 1D model runs in MATLAB, and the main design criteria are sufficient water infiltration to avoid flooding before the basin level, and sufficient residence time and retardation of selected environment impact chemicals to give time to treat these pollutants. The preliminary tests indicate that the proposed model successfully identifies filter medium design parameters capable of meeting the both criteria. And this work has resulted in a promising modeling platform for designer soils in SATs, which will be further tested and refined by the University of Aalborg. you have here some of the results of the model on water depth and also in chemical breakthrough. And you can see more of this last work in our deliverable 8.5, and I leave here a link for a related publication of INSA Lyon. Where to find all of these links in these slides? I think that we are going to share this after the webinar, and you can also go to the Co-UDlabs web in the dissemination part section, and you can see the deliverables and publication, and also in our Zenodo community of Co-UDlabs, you can go here and go to and search the publication that you are interested in, and also filter by project deliverable dataset or presentation journal, as you want. So thank you very much. Hope not to go very late. And now it's turn for James for presenting us their experimental campaign on Coventry University.
Thank you. If you could stop sharing, Juan.
Yeah.
And over to you, James.
Hello, everyone. Yeah, sorry, I seem to have my camera looks a bit green. Oh, it's getting better now. Right, let's see if I can share. Yeah, there we go.
Not seeing your slides yet, James.
Hang on.
Oh, almost right. We've got, yes, that's it.
You're
on.
Good.
You're sounding a little bit echoey. I don't know if you could come a little closer to the microphone or.
It's just how I sound normally, and I'm just an echoey sort of person.
Okay, over to you.
Hopefully you can still hear me. Okay, so Juan mentioned I was going to talk about a couple of deliverables. I'm going to immediately disappoint everyone by only talking about one of them. So we also did some work on energy losses, but in the interest of time and the fact that this presentation or this topic has slightly nicer videos, I thought I'd concentrate mainly on this second bit of work that we've been doing at Sheffield concerning the transport of contaminants from urban drainage systems to urban services during flooding events. So just to start with a little bit of context. So researchers, academics, and people are generally getting more interested in not just what are the sort of hydrodynamic effects or the hydrodynamic risks of flooding in terms of water volume, but also what is sort of contained within that floodwater, particularly in urban areas. So I've got a picture over here of somewhere very close to where I live, just down very close to my house. It's a playground, and this particular site floods quite regularly, and you get water coming out of a drainage system, so surcharged water coming out of the drainage system. And I had one of my PhD students go down and do some sampling with the help of one of my colleagues who's more interested in microbiology than I am, or more skilled in microbiology than I am. And you can sample this water and you can basically work out that it has all sorts of different contaminants in it. So this picture down here is too small to see, but basically each color bar in there is basically a different type of microbiological contaminants. Some of them are harmful, some of them are not harmful, but there's a whole array of things living in our floodwater that we generally wouldn't necessarily want to come in contact with. So that's generally the context. And what we're kind of interested in doing is, can we have a better job of understanding and quantifying the risks to public health of coming into contact or being exposed to some of these different pathogens. So over the last few years, people have started to try and sort of model this this process. So they're interested in sort of saying, where are the areas of contamination coming from in urban drainage networks during floods? So generally it's your surcharging urban drainage systems or other areas that might have microbiological pollutants. And can we model the sort of transport of the surcharging water within the sewer network, within the floodwater, to work out where does the contamination end up, where are the particular hotspots of particular contaminants. However, obviously there are also a lot of uncertainties and unknowns within this process, pollutant behavior, dispersion, how the different pollutants behave within floodwater? Do they attach to sediments? Are they soluble, etc.? So as part of Co-UDlabs, what we've been doing as part of this bit of work is, again, providing, using some of our experimental facilities to provide open access data sets to try and help model testing and model validation. And at Sheffield, over the last couple of years, we've had a couple of activities, both in the joint research activities and also the transnational access activities, that have been looking at trying to understand transport processes within shallow urban floodwaters when you have a surcharging urban drainage system. So we've been collecting experimental data and basically trying to make that open access so that people can start to have at least some data to start to do model testing and validation. So this is just a little picture of the facility we've been using. So we've been using this for a number of years. Video here. Basically to look at interactions between pipe flows and surface flows within floodwaters. So we have a pipe with a manhole, and in the test that I'm talking about today, we basically set the manhole to start to surcharge. So you have flow coming, excess flow coming from the pipe network and surcharging onto the surface. And you can also set a sort of a shallow urban flood flow on the top. So you have about 10 or 20 millimeters of flow coming as sort of urban runoff as well on the top. So you can look at the interactions between the surcharging surface flow and the surcharging flow from the pipe and the surface flow. And as I said, we've been using this facility for quite a number of years, but within Co-UDlabs, most of our work's been starting to use this to, again, start to look at maybe, can we look at pollutant transport processes within this particular system. Moving on. So, first bit of work we did a couple of years ago was start to look at sort of soluble contamination. We had transnational access visit from a team in France and someone in Exeter as well, who came and were interested in, firstly, how can we measure this within a lab facility? And then, as I said, can we provide some more open access data for modeling approaches? So what we do is essentially put a tracer into our pipe system, restrict the valve or restrict the flow downstream of our manhole, and get the flow to surcharge onto the surface. And then what you're trying to do is essentially track the concentration of tracer within your surface flow. And we used a couple of different methods to try and do this. So the picture I put up here is actually our attempt to use hot water as a tracer, and then use a thermal camera to look at the relative heat difference between the surcharging water and the background water. And from that, you can work out what proportion of water is coming from concentration of polluted water, you might say polluted water, and surface flow as well. So the pictures I've got here, you can kind of see at the top is one just after the hot water has been injected in here, and it's just started to emerge from the manhole and started to spread in the surface flow. So I think this is 5 seconds after ejection, and then 10 seconds after ejection and 20 seconds after ejection. So you can see the hot water spreading within the surface flow, which is traveling from left to right. Also, on here, we have placed a couple of obstructions within the flow, so the water flows around and through different obstructions. So we tested different obstructions within this data set. So we have different arrangements. And the one displayed here is kind of when you have alternating blocks. So the water is forced around in between these particular blocks, and it sort of causes the water to the contaminant to sort of pond upstream. As well as this, we also measured surface velocities using SPIV, which is similar to the pictures that sort of Juan showed you earlier. So that was one technique we used. On the next slide, I have a picture of a similar sort of experiment. It's a different setup in that we don't have any obstructions, and this one is done as a video. And in this case, we don't have any obstructions, so it's just water coming out of the manhole and spreading downstream without any obstructions downstream. In this particular case, we used a different experimental technique. So in this case, we're actually dyeing the water. So we're putting dyed water into the pipe flow, and then using a camera above to look at the sort of intensity of light from the different spectrums, color spectrums you get as you move downstream. And again, using that to work out the concentration at different points in the image, which is quite tricky to achieve because you need quite a complicated calibration. And you can see the method works reasonably well, apart from a few particular points where you have interactions between different cameras that are joining together, and you get certain sort of flickering effects. So what we did as part of this work is compare these different methods and try and look at advantages and disadvantages of using the different techniques. Overall, they worked fairly similarly in terms of looking at the overall extent of where the pollutant ended up. There were some differences caused by local errors, particularly in the dye camera, and also some slightly different gradients we observed between the two techniques, which may be a function of the fact that the heat method isn't a conservative pollutant. So we have quite a few different tests with different hydraulic properties, so different degrees of surcharge, different surface flows, and different layouts of obstructions. And that's been made available as an open access data set. And also there's a paper which is currently going through the review process, which explains all the different aspects of the tests. So having done solutes, we then sort of moved on to start to look at sediments. So essentially we're interested in, can we start to think about how the sediments in your urban drainage system firstly exchange to the floodplain, and then where do they spread on the surface? So this is a little bit more recent, and some of this work is a little bit more preliminary. But what we've essentially been doing is injecting a mix of sediments and water into our sewer flow. And then the first thing we looked at was essentially trying to quantify how much of the sediment load exchanges to the floodplain and how much continues in the pipe for different degrees of obstruction in the pipe, and also hydraulic properties. And also we looked at the influence of having different types of manhole lid on the surface and how that affects how much sediment gets exchanged to the surface. So there's a plot here which basically is a bit of an overview of some of the work we've done so far. And essentially this plots the proportional exchange of flow against the proportional exchange of sediment. So essentially how much sediment of the initial flow, of the initial sediment load, how much is going up and how much is going through as a function of how much of the flow, how much of the water is going up and how much is going through. So on here you have a line of equality up here, which basically if your result lands on this line, it means that the sediment load going to the surface is exactly the same as the flow going to the surface. And you can see, as you would expect, the sediment load going to the surface is less than the flow because the sediment is of a higher density. But there are a couple of interesting effects to observe on this particular case. The first is the influence of the manhole grate you put on here. So on this particular example, the black dots on the top are essentially the experiments where you don't have a manhole grate, and the other tests are the different other colors are the different manhole grates. So you can see that adding a manhole grate reduces the proportion of sediment that is ending up on the surface by about 10%, I would say, compared to if you have a manhole grate, which is reasonably consistent. The other thing to note is the existence of what we would say is kind of a threshold. So in our particular case, for most of the flow up to about 40% of flow exchange, you have about 10 or less than 10% of the amount of sediment moves to the surface. So up to about 40% flow exchange, you have about 10% sediment exchange going to the surface. But that changes and you get a sudden rapid increase in the amount of sediment being pushed to the surface as you go along, as you go above about 40%. And you get this sudden increase in the amount of sediment being pushed to the surface. So this is something we're sort of continuing to investigate. I have a PhD student who's carrying on working after Co-UDlabs is finished for about a year or so. So we're doing a little bit more work on this. However, the results that we've got so far are in this deliverable 8.3, so people can have a look at those experiments. And the final thing I wanted to show is that we've been also trying to look at what happens to the sediments when they reach the surface. So in terms of where they deposit within the surface flow. So what we've been doing is initially just using cameras to look at what happens in terms of where the sediments deposit around the manhole. So what you've got here are a couple of pictures looking straight down from the roof of the facility, looking down onto the manhole, and you can see the deposition patterns of sediment after 2 of the tests we've done. So the pictures in the middle are kind of the raw images, and then what we can do is essentially process those, get rid of the fact that the images are distorted by correcting the image, taking out the manhole, and you end up with kind of a map of where the sediments are deposited. What I've done here is just show you 2 different examples or 2 different tests with 1 specific difference. So the one on the top essentially has no surface flow, so no flow coming in from the surface. The one on the bottom has exactly the same amount of surcharging flow and exactly the same sediment load, but you have about a 20 millimeter flow on the surface. So you can see there's quite a different pattern in terms of both the concentration of sediments, in terms of where they are, and also the sort of the distance they travel from the manhole. So we're carrying on doing a bit more work on this and trying to look at where the sediments will end up when you have a range of different conditions, and what happens if you have obstructions on the surface, different grades of sediment, and also looking at the shape of the sediment as well as something we're interested in carrying on. Okay, so overall conclusions. We know that sewer surcharge and overflow events carry pathogens and other contaminants. However, understanding the transport of these materials is very challenging in both lab and field conditions. And what we found from doing our tests is that the transport pathways where the contaminants end up are very, very sensitive to the flow conditions and the local geometrical features of the network. So if you have obstructions, what does the surface flow look like? Where do the velocity fields go? So what we've been doing in Co-UDlabs has been, we've been looking at both soluble and sediment material transport from a surcharging manhole using our scale model. And we have produced and we are still producing data sets which will hopefully help with model testing and validation, so we can have a bit more confidence in model predictions that try and understand these processes. I should have said at the start, obviously it's not just me that's done all this, there's been quite a few people that have contributed to this work as well. So I've put their names up here, various people who have helped out in either transnational access projects or the joint research activities. And I think that's me finished.
Thank you very much, James. And if you stop sharing, then we will move on to our final presenter, João.
Yeah.
And yep, we can see your slides there. Oh no, we've got your.
You can hear me and see me, but no longer the slides.
No, we got.
How does it look
now
like?
we can see the slides. Jolly good. Okay,
it's good. All right. All right. So just before lunch break, I would say, I would like to present some work that Prabhat Joshi, a PhD student here at EAVAG, conducted an experiment with the colleagues from the University of A Coruña, trying to understand the influence of litter and sand on the water balance of blue-green infrastructure. So basically, the idea or the motivation for this study was that there's many studies and guidelines that emphasize the design, the planning, and the implementation of blue-green infrastructure. However, we tend to forget that this is an infrastructure as well. So, for example, we have guidelines, as I said, from Syria on how we develop these things to make them high performant, nice looking, and so on. We have various studies in the literature showing that where we should implement these infrastructure, these elements to, for example, reduce flooding events, to reduce the CSO discharges. we also have in the literature studies looking into the performance and of different of types of this infrastructure. However, we tend to, as I said, forget that these elements are also infrastructure, are more than just a tree or a grass or a green infrastructure or green aspects, is also an infrastructure. And here, just with these two images generated with AI, just to illustrate what I'm trying to say. So basically, we design things and having in mind that this will be nice with water and green and greenery. But then what happens, or what can happen, if we don't really keep an eye on this infrastructure, that these nice looking things after some years may become problematic, or more important for us when we look into the performance, they do not perform as intended at the beginning. And specifically, the picture that we see on the right hand side here is that it's very common, unfortunately, in various city contexts. And because at the end, and frequently people tend to use these, or sometimes then use these areas as a deposition of waste or discarding materials and so on. So keeping an eye on how these systems can perform over time, it's, in our opinion, quite important to make sure that they still perform as designed, and also to understand the need for maintenance, how frequent they need to be checked, how they need to be evaluated. So this is the goal. And we went, or Prabat went to A Coruña to have an experiment in the lab. And before, we've seen some pictures and videos from Juan on this lab in A Coruña, where we do have the possibility to have a rainfall generator. So here we had the rainfall, and basically we assume that we have a normal BGI as designed with the different layers, and also we could clog or change the characteristics of the blue-green infrastructure, and then compare the under drain flow hydrographs to understand the performance of these elements. As I said, we went to Prabat went to A Coruña, working with the colleagues from there, also involved in the Co-UDlabs as a joint research and activity. And we had the rain generator. We had access to BGIs that were mainly green roofs, but we used the green roofs as an example of a BGI, having the different surfaces, the under drain flow, possibility to have runoff, and so on. And we actually play with leaves on one side to have the surface sealed, and also with sand to try to replace or mimic a clogged substrate. And then we installed soil moisture sensors, and we measured the under drain flow. This is the water balance components of typical BGI. So we have the rainfall and the surface inflow as inputs to the BGI. We have then the losses as evapotranspiration, the overflow. We also have ponding. We have exfiltration, and we have the under drain flow. In the lab, we have to say that we significantly simplified these elements. So, for example, for the rainfall, we have fixed intensity and duration. We did not have the surface inflow. Also, evapotranspiration were assumed minimal. We did not consider because we are in an indoor environment. We avoided to have overflow and ponding. And we measured then the wet conditions and the drain flow. So this was the idea of the experiment. And in this slide, we have this as an example of a box with a BGI with some vegetation, and on the right-hand side we see Another one used as, again, as reference condition, but with slightly different vegetation growth. And as for the benchmark, we run the system a few times, and we could see, as expected, we have the rainfall as this constant rainfall block. We run the system several times, and as you could see, we have a delay in the under drain flow, and the system does not react exactly the same way. So there's some uncertainty there. Nothing special here, just to illustrate this is really our benchmark that we're going to use later on. And then we had these addition of sand and solution of leaves to answer how does leaf litter and sand accumulation affect the BGI's water balance. So this was really our question. And basically we added sand into the green roof or into the BGI with different amounts of sand spread more or less evenly throughout the tray. As you can see here in the pictures on the right, no sand and a little bit more sand, and almost vegetation disappearing in the bottom photo. And what we could see here is that compared to the benchmark, we could see that the under drain flow it decreases by when we added the sand accumulation. So what we could see, there's a delay, a slight delay into the onset of the under drain flow with more sand when we added sand. The reference or the benchmark data set is the grayish symbols or circles in this case, whereas the experiments with sand are the colored lines. And what we could see is that by adding the sand, we do have less under drain flow, more or less expected. We also play with dry and wet sand, and we had more or less the same output. When we looked into the leaves, and here we can see one of the examples on this video on the left, we had expectation by sealing the surface, something else would happen. And again, similar experiment, we had different amounts of leaves into the tray. And more or less similar things did happen with the leaves. And basically, the amount of under drain flow was reduced. And I have to add here that there was no runoff, so there was most likely more ponding and the more retention capacity by adding leaves and also sand. So it was a little bit a surprise result from these experiments that by adding leaves or adding leaves on top of the substrate can help reducing the under drain flow and then keep more water into the system for longer. So then to try to summarize how does leaf litter and sand accumulation can affect the BGI's water balance. So we could see that under drain flow was delayed and reduced and storage was increased. This was somehow, sorry, I had to stop the blinds. It was a positive change in the hydrological and hydraulic behavior of the BGI, but also can pose some waterlogging issues in the long term. And also increasing the soil wetness could yield higher surface runoff after longer rainfall events. So we published the data set. It's available. In a minute, I will come to the link where you can get access to the data. But what is the value of these experimental data? So, as I said, quantifies the effect of clogging and surface sealing on BGI performance. Hopefully helps us to understand the influence of shock events that bring high amounts of pollutant loads later on as a possibility for following research. Also supports validating models that simulate the influence of incremental sediment buildup. So more work that can be done on top of this data set, and also sheds light on the monitoring and maintenance requirements of BGI. As an example of these future research avenues, Prabhat continued to work on his PhD and then developed a methodology, or has finished, is now in process of publishing or submitting for publication the work. The question is, if we do have a BGI and we would like to know if it's in real life, and it's we would like to know if it's performing as designed, it's difficult because we can have the BGI implemented now for a specific rainfall event, but then this very specific rainfall event may not, or most likely will not, happen in the future. So then what Prabhat did was really to develop a methodology to identify similar rainfall events from different periods of the time series, of a rainfall time series. And he has done it and then started to compare the BGI performance when using similar rainfall events from different periods using a real rainfall time series. And as we can see in these line plots on the left, even that when the rainfall events are statistically similar, the under drain flow hydrographs can be significantly different. Prabhat also did this thing with using synthetic data, using a model, and could confirm that the distribution of these events can be significantly different. So it's a robust method to identify possible changes in hydrological performance. Prabhat also used a real data set from Oslo during 5 years and could find 2 similar rainfall events separated by almost 5 years, and then there also could see significantly significant changes in the under drain flow. Coming to the end, so this experiment was really interesting to see how BGI's performance could change over time. The sand accumulation and leaf litter accumulation affected the water balance, slower and smaller under drain flow. And then the results, I would like to, or we would like to use these results to emphasize the need for BGI monitoring and maintenance in a similar fashion that we look into pipes and pumps and the more conventional elements of drainage systems. And as promised, for those who are interested in the data or the main findings of the experiment, you can access them openly through these links and through you can search for this on the internet. And that's it. Thank you.
Thank you to all 3 of you. And I found your AI generated slides showing the ideal situation and perhaps the reality. They were particularly good. And it does sum up and pull together quite a lot of what the 3 of you have been presenting there. Going back, for example, to the permeable pavements which get clogged. People forget that permeable pavements over time deteriorate and get clogged. And then what happens with a green roof? There will be an accumulation of various materials which may clog it. So it's something which I think a lot of people are very much aware of, is that all of these systems for dealing with surface water runoff do require ongoing maintenance. And it's been one of the biggest, it's one thing to build them, and to find the funds to build them and to install them. It's then a question of who is responsible and where does the funding come from. That's sort of my observation from this.
Yep.
I don't see any questions in the chat.
Yeah, just a quickly reacting to your observation, Ian. I fully agree. And then something that I did not mention, right? So if we really want to go in this direction, which I think we need, or we should, we need to also think about sensors. How do we install sensors to monitor these sites? There's a few examples in research that I know for long-term monitoring, like in the US. But having this infrastructure monitored, it will be also a challenge, I would say. But well, step by step.
I think you're right. I was looking. I'm obviously based in the UK, and speaking to one of our water companies the other day, to somebody who's now responsible for their sustainable drainage systems. So she manages everything from green roofs down to retention basins and drain systems. And she is relatively new role, really focused on trying to work out how do I maintain these for the next few decades. And I think, as you mentioned there, sensors, some way of the sensors that we've been looking at for sewers are equally as applicable to the operation of sustainable drainage.
Yeah, it will be a challenge that will come soon.
It will be. It will be. I was going to ask you, Juan, what would be, from the results of all of this work you've done over the last 4 years and in this whole joint research activity, what would you say would be your main takeaways if you had to think up 2 or 3 bullet points of what have we learned most from this exercise?
Okay, I think that is a hard question. As you see, we have done a lot of different things in different research lines. I think that all of them are quite interesting and needed, actually, because they are very related with this intention of or needed for monitoring our urban drainage systems and urban surfaces. And I think that that is the direction that we are taking now, the digitalization of this monitoring and the trade of the data that we are collecting. But I think that the main takeaway from this joint research activity is the joining efforts from all the partners and the collaboration to overcome all of these challenges that we have.
Thank you for that. And really, perhaps pulling the let's just quick check the chat again. No, nothing specifically in the chat. So sort of pulling together the 3 sessions from this morning. What we have attempted to do here is to give a flavour of the scope and the scale of the work that we've been undertaking with the Co-UDlabs, and particularly today. And for those of you who've been attending, listening to this for the first time, an overload of web links, because there is an awful lot of information and data which has come out of this project, and we want to try to ensure that it is widely disseminated. So with the remaining part of the Co-UDlabs project is now focused very much on completing all of the outputs and its legacy. And many of us here today, from the speaker side, we're meeting again next week. We have an event, an info day, actually in Brussels with the European Commission to highlight what has come from this research project. And I would also just remind you that beyond Co-UDlabs, we have the UDrain collaboration, which has been started, and we will be looking to find ways to continue with this, the work of this consortium. So this is seen very much as a sort of a first step to bring together research facilities and capabilities from across Europe to demonstrate through a wide variety of transnational access projects the value of conducting research, and through our joint research activities to deliver a whole variety of extremely useful outputs to the project. So thank you, everybody. And I'm delighted that we are finishing 1 minute before time. Thank you all, and enjoy your lunch. Cheerio.
Thank you. Bye-bye.
Bye.